We're starting chapter 19, which is confidence intervals for proportions. So the rest of Unit 5 is going to focus on proportions instead of means. In chapter 18, we learned about sampling distribution models for both proportions and for means. But pretty much from here on out, we're only going to focus on proportions, and then when we get to Unit 6, we'll go back and look at means again. So for now, we're looking at confidence intervals, specifically for proportions. Before we get into talking about confidence intervals, though, I want to talk about standard error. So if we recall from chapter 18, standard error is actually standard deviation that's based off of an estimate. We learned again in chapter 18 that both the sampling distributions we've looked at are normal, and for proportions, the standard deviation is the square root of PQ over N, and for means, the standard deviation is sigma over the square root of N, where sigma is your population standard deviation, and P is your population proportion. So if we don't know what P, our population proportion is, or sigma, our population standard deviation is, then we're stuck, right? We can't move forward if we don't know what the population really is. Nope. We'll use the estimate instead. Whenever we estimate the standard deviation for a sampling distribution, we call it standard error. Again, it doesn't mean that there's a mistake. It just means that it's an estimate instead of what the actual population is. So then, in that case, we calculate standard error instead of standard deviation. And for a proportion, we end up that the standard error, which now is SE instead of SD, and it's the square root of P hat Q hat over N. So the equation didn't change, except now it's P hat and Q hat, because it's the proportion that we get from our sample, not the population. For a mean, the standard error ends up becoming S over the square root of N, and again that's S instead of sigma because S is the standard deviation that we get from our sample. So again, in both cases we're using what we get from our sample and not the population, which is why it's standard error, because it's based off of an estimate. Moving on to confidence intervals, we're going to jump right into an example. So a CFAN disease team sampled 104 CFANs at random in Las Redes Reef in Acumel, Mexico, and I'm sure I butchered all of that. They ended up finding that 54 of them were diseased. This gives us a proportion of P hat, and it's P hat because it's from a sample of 54 out of 104, which is 51.9%. What we want to know, though, is about the sampling distribution of the sample population of infected CFANs. We're trying to figure out, are 51.9% of all CFANs infected? And we actually can't tell that based off of the information that we have. We only know our specific sample. We don't know about the population of CFANs as a whole. However, we can end up using confidence intervals to help kind of narrow it down for us. So continuing with a confidence interval, we know that it'll be approximately normal, and the mean of the proportion of infected CFANs of this sample is 51.9%. Now we know it'll be approximately normal, not just our one sample, but if we were to do an infinite number of samples, then we know that the model of all samples will be approximately normal. Does that mean that the infected proportion of all CFANs is 51.9%? No, absolutely not. Again, that's just our sample estimate, so that's just P hat. That doesn't tell us that 51.9% of every single CFAN out there is infected. We just know from our sample that's what we got. However, we also know some other information. We know that the sampling distribution model is going to be centered at P, the true proportion. And we know that the standard error is calculated as the square root of P hat Q hat over N. And we can actually end up calculating that out and getting 0.049 or 4.9%. So again, when we're dealing with proportions, you will end up with smaller standard errors, and don't worry about that. That is okay. Now, what we can do, using the concept of sampling distribution models and knowing what our sample proportion is and what our standard error is, we know that our sampling model will follow the normal model. And you guys are going to have to bear with me because I'm going to try using pen here. And we will end up with the mean should be at 0.519. Then one standard deviation above that, I would add the 0.049 to it, and we would get 0.568. Two standard deviations, again, I would add the 0.049, and we would get 0.617. And if I am 3 standard deviations above the mean, I will be adding 0.049 one more time, and we end up at 0.666. Going the other way, one standard deviation below the mean ends up being 0.47. 2 standard deviations below the mean ends up being 0.421. And 3 standard deviations below the mean, again, we would subtract the 0.049 and we get 0.372. This is what our sampling model should end up looking something like. Now, our mean is not exactly correct because it's based off of our sample and it's only an estimate. It's not the true proportion. But what does this tell us? Because it's normal, we know that 68% of all samples of 104 CFANs will be within one standard error, which was 0.049, and it will be within one standard error of our sample. 95% will be within 2 standard errors, or 2 times 0.049 of our p-hat, and 99.7% will be within 3 standard errors, or 3 times 0.049 of our sample proportion. Again, this still does not tell us what the value of the population proportion is. We still don't know that population proportion. However, we can, using our 68, 95, 99.7 rule, using the 95, because that makes us pretty confident, we can be 95% sure that it is within 2 standard errors, or 0.098, because I multiplied 2 times 0.049, of our sample proportion. So the best thing that we can do to find the population proportion P is to find an interval. Even then, we're not 100% sure that that interval will actually contain our population proportion, but we can be confident enough. So then what can we really say about P? Well, by adding 0.098, which is 2 standard errors, and subtracting that value from our sample proportion of 0.519, we can end up saying that we are 95% confident that between 42.1% and 61.7% of the laceratus CFANs are infected. That statement right there is called a confidence interval. And this is pretty much exactly how you will interpret a confidence interval every single time you have to interpret one, which from here on out will be fairly frequently. So you give how confident you are, you state what the interval is, and you put it in context. So we are 95% confident that between 42.1 and 61.7% of the laceratus CFANs are infected. I can't say of all the ocean CFANs because I only took the sample in one area, so I can only focus on that one area. There are many different kinds of confidence intervals, and we'll end up talking about quite a few of them, but this one in particular is called a 1 proportion Z interval. I'm going to use this little diagram because I think it's funny, and I think it helps. It's Acme P-trap, guaranteed, little asterisk, with 95% confidence to capture P. So P is our population proportion. So if you know this guy is holding a sign in between 2 things, p-hat right in the middle, minus our 2 standard errors, plus our 2 standard errors. Our population proportion will be somewhere in this red-lined area. Reaching out 2 standard errors on either side of p-hat makes us 95% confident we'll trap the true proportion. So what does 95% confidence really mean? So each confidence interval uses a sample statistic to estimate a population parameter. Since samples vary, so again, that team could go out and draw a second sample of 104 CFANs or a third sample of 104 CFANs and so on and so forth, and every single time they might get a slightly different proportion. We would expect that. We expect there to be some variability. What that means, though, is that each sample will end up creating its own confidence interval. So our confidence intervals end up varying as well. This figure on the right shows that some of our confidence intervals will capture the true proportion, which is our green line right here, while others do not. So the red dots indicate what the sample proportion is. The blue lines indicate what the interval itself is. And then the green line represents the population proportion. So there are 20 different samples here. So they made 20 different confidence intervals. And as we can see, the first one ended up not catching the true proportion. The next few did, and then it didn't again. And the next few did, and then it didn't again. And then the rest of them also did. Each confidence interval, it might actually catch the population proportion. But then again, it might not. It just depends on how far off your sample statistic is. What this is really saying is that our confidence is in the process of constructing the interval, not in any one interval itself. We're 95% confident that our process worked, not necessarily that the actual value is in that particular interval. Thus, we expect that about 95% of all 95% confidence intervals to contain the true parameter that they're estimating. So if you were to do 100 samples and make 100 different confidence intervals, each with 95% confidence, then 95 of those intervals should end up containing the true proportion, and 5 of them will miss the mark. That's what the 95% confidence actually means. So again, it's in the process, not the actual interval itself. That is all we have for tonight. I will see you guys tomorrow in class. Have a good night.